Hi everyone, thanks for coming to my session on making the JDK more secure. My name is Sean Mullan. I'm the JDK Security Group Lead. I also work for Oracle. And if you want to follow me, my Twitter handle is Sean J. Mullan. I mostly tweet about Java security stuff, so it's a good way to keep up to date on what's happening in this area as we go forward. So of course, the first thing I need to show is the obligatory safe harbor statement. So here's my agenda. Just before we get started, how many people here are familiar with Java security? Raise your hands. Okay, more than half of you. How many people consider themselves experts in Java security? Raise your hands. Just me and one other guy? Okay. Well, the good thing is you don't need to be an expert in Java security to get something out of this talk. What I like to do at the beginning is just give a quick high-level overview of Java security. There's a lot of components that make up Java security, so I feel it's a good way to, as a refresher, and also sets the stage for the rest of my talk because I will be discussing about most of those components in a little bit more detail. So what I'm going to do is start out with an introduction and goals, and then I'm going to go through the improvements that we've been making to make the JDK more secure by default. Then I'll talk about some of the exciting new security features in the just released JDK 9, and then we'll wrap up with the conclusion and pointers to more information. So before I go into the introduction, I just want to tell you a little bit more what I mean about making the JDK more secure. Why isn't that? Okay, here we go. So it really can be broken down into two primary goals. The first goal is to provide you with a secure by default environment when you initially install the JDK. So we want to provide a default configuration that makes sure that you're properly restricted by algorithms that are either weak or broken or essentially are no longer safe to be trusted. We really want to reduce the risk of attacks to your applications, especially if they're processing data over the internet and that internet may be susceptible to attack. That data may be a susceptible attack. The second goal is to deliver new features that keep up with the rapidly evolving security landscape. Anybody that works on security knows the landscape is changing rapidly. Algorithms are being broken, new ones are taking place, so we can't sit on our hands. We want to deliver the features to you that helps you build security into your applications and meets the requirements of today and the future. So my hope is that you come away from this presentation that you have a strong feeling that we're committed to both of these goals and helping you deliver secure applications. So here's my one-slide overview of Java security. No, just kidding. What I'm going to show is a diagram of the different components that make up Java security. So at the lowest layer, we have the Java language and runtime security component. So these are the things that are built into the Java language that allows you to create more robust and secure applications. So things like automatic memory management, different language access modifiers, type safety, and so forth. And then there's features at runtime, such as the bytecode verifier. Make sure your bytecodes are well-formed and have not been tampered with. And then optionally, you can also enable a security manager at runtime. And the security manager acts as a central authority for protecting your sensitive resources from potentially untrusted code. Above this component, we have a large set of APIs and libraries that allow you to build security into your applications. Let's just look at each one of these in a little bit of detail. So over on the bottom left, we have the JCA, also known as JCE, which is our low-level APIs for cryptographic operations, things like message digests, digital signatures, and so forth. To the right of that, we have a PKI component, also called SIRPath, and these contain APIs for parsing and validating chains of certificates and so forth. Above that, we have something called the Simple Authentication and Security Layer. In the middle, we have APIs for JSE. That includes our APIs for SSL, TLS, and DTLS, which is brand new in JDK 9. I'll be talking about that a little later. Over on the right, we have APIs for verifying signed jars. And up at the top, we have an API for the Java Authentication and Authorization Service. So this allows you to do things like user-based authentication and authorization. And in the middle, we have GSS API and a Kerberos implementation underneath it. And over to the right, we have APIs for XML signature, verifying and generating XML signatures. Now, the nice thing about all these APIs is that they are provider-based. And what this means that you're able to plug in different implementations of different algorithms. So the JDK itself includes implementations of all the well-known standard algorithms and a few more. But you're free to go out, use a third-party service provider, implement your own service provider. So it's very flexible and extensible in that manner. And then finally at the top, we have a small set of security tools for managing security. We have Key Tool for managing the contents of Keystores, certificates, keys, and so forth. Jar Signer for signing and verifying jar files. Policy Tool is a clunky graphical user interface for editing policy files. It's actually been deprecated, and we're going to be removing it from the next release of the JDK. So I wouldn't start depending on it now if I were you. And then all the way to the right, we also rebundle the standard Kerberos utilities, KInit, KList, and KTab on the Windows platform. So that's Java security in a nutshell. So for the next part of my talk, I'm going to be discussing the improvements we have made to the JDK to make it more secure by default. So what are the specific goals? They can be broken down into 3 different goals when we talk about making the JDK secure by default. The first is to restrict weak algorithms and protocols by default. So here we look to industry standards, recommendations for deciding when an algorithm can no longer be trusted and when we should start deprecating it. We also look at other products, what other competitors and vendors are doing to make sure that we keep pace with them. So an example here is when we restricted jar files that are signed with MD5. MD5 can no longer be trusted for digital signatures. So these jar files are now treated as unsigned jars. The signature is effectively ignored, so it can't do any damage on your system. Any permissions that are granted to it will be ignored. The second goal is to ensure our defaults remain strong. So the JDK, various APIs, tools, and some of our implementations fall back to default algorithms if you haven't specified a specific algorithm. The problem with that, it's done for user friendliness, so you don't have to remember all these algorithms, but the problem with that is what was secure or strong when it was originally made the default usually doesn't last over the lifetime of a JDK release. So an example of where we changed something is we changed the default settings for Key Tool and Jar Signer were changed from SHA-1-based algorithms to SHA-2-based algorithms. And then finally, the third goal is to add support for stronger algorithms and protocols. We try to ensure that every single security operation or function has at least one strong choice or alternative in the JDK. And again, the history of a JDK support release can span many years. So often what we have to do is backport support for stronger algorithms from later releases to earlier releases to ensure that those earlier releases have as much security as the later releases. So an example of this is when we backported support for TLS 1.2 to JDK 6. So now with JDK 6, you can use TLS 1.2 by default instead of relying on the less secure TLS 1.1 or 1.0 protocols. Okay, the cryptographic roadmap. Has anyone seen the cryptographic roadmap at that URL? Raise the hands. Oh, wow, okay, a few of you. Okay, so the cryptographic roadmap was about a year ago initially published on August 18th, 2016. What we found is that while we're working on these changes to make the JDK more secure by default, we needed a better mechanism to tell you, the users, that these changes were coming. In other words, a heads up. Many of these changes have some compatibility impact, so you need to be aware that they may be coming in case your applications may be impacted. So one of the primary goals of the crypto roadmap is to provide guidance to you for determining if a change may impact your applications. So we provide tips, tools for determining, hey, SHA-1 is going to be restricted in 6 months. How do I know if I'm going to be infected? So we try to provide tools and tips for you to figure that out. The crypto roadmap also shows all changes that have been released in the past 1 to 2 years. So if you want a historical perspective, you can go through all the changes that we've made, and there's quite a lot of them in the last 1 to 2 years. And very important, changes may not apply to third-party security providers. So if you're using a third-party security provider, check with them to make sure, see if they're complying with these restrictions. So here's a couple snapshots of the actual crypto roadmap today. The first is just the banner at the top of the site, and the second is the top of a table which shows our planned changes upcoming in the next 3 to 6 months. I just wanted to go through the different columns in this table just to give you an idea of what's actually in that table. So the table contains 1, 2, 3, 4, 5, 6 columns. The first 2 columns are the date and the release that the change is targeted to. And then the next column is the algorithm or protocol that is impacted or will be changed. The fourth column is the action. What are we doing? What is the change? And then the 5th column is how to test or enable the change. So how do I know if I'm going to be impacted by this change? Typically, that's a pointer to another document that contains more information. And then finally, there's a change log showing what if we've made any changes to the entry since it was put into the roadmap. So let's just go through the very first example. October 17th, which is only about 2 weeks away. And the targeted releases are JDK 6 and R28. Does anyone know what R28 is? Oh, JRocket, yeah. So we still support JRocket, so it's still up in here on our roadmap. The particular algorithm and protocol that's being affected is the DSA public key algorithm and the SHA-224 with DSA and SHA-256 with DSA signature algorithms. What are we doing? We're adding support for the SHA-224 with DSA and SHA-256 with DSA signature algorithms and DSA keys with sizes up to 2048 bits. The reason we're doing this is prior to this release that's coming out, for DSA keys, we only support SHA-1-based signature algorithms and DSA keys with a maximum size of 1024 bits. Both of those are considered somewhat weak and somewhat risky. There's been published weaknesses in those key sizes and signature algorithms. So we want to provide you with a strong alternative if you're using DSA keys. This is an example of adding support for stronger algorithms. I meant to say that these changes are already in JDK 7 and later, so don't worry about that if you're using those releases. Since this is a new feature, there's nothing you need to do to test it. Just when it's available, start using it. And it hasn't been changed since we first announced it. So the roadmap contains a lot of changes. I don't have time to go through all of them today, but I thought I would pick out two of them that I thought were the most significant for you to hear about today. One of them is one that we've already released, and the other one is one that's almost being released as of today. I'll let you know. You'll see in a minute. So the first one is disable SHA-1 certificates. So here, what we've done is we've disabled or restricted by default SHA-1 TLS server certificates that chain to public root CAs are now restricted by default. This restriction is already in JDK 9, and it's already in 8U141, 7U151, and 6U161. Those releases were released in July. This restriction applies to all certificates in the chain, so not only the server certificate, but any intermediate CA certificates that may follow. If they use SHA-1, the chain will be blocked as well. And revocation information. If you download OCSP responses or CRLs that are signed with SHA-1, also the validation will fail and the certificate chain will be blocked. When I say public root CAs, I mean the ones that are pre-installed in the CA certs key store when you initially install the JDK. So if you're using your own enterprise CA or self-signed certs, this restriction's not going to apply. You can go into the, I'll show you later, you can go into the properties and make it apply to any root CA. But for now, we wanted to keep the compatibility risk. Enterprise CAs usually take a little bit longer to adapt to restrictions, so we're giving them more time. This particular restriction adheres to the CA Browser Forum, which is a forum of CAs and browsers that come up with ways to use certificates more securely. They say, effective 1st January 2016, CAs must not issue any new subscriber certificates or subordinate CA certificates using the SHA-1 hash algorithm. And more information about this feature can be seen in JEP 288. So this was actually a JDK 9 feature, which we then have backported to our earlier releases. Okay, this is a little bit of a quiz. Have any of you ever written code like this? And if I compile and run it, what do you think the result will be? It's generating a 256-bit AES secret key, and then it's trying to encrypt some data with it. Anyone? Anyone know? Okay, well, it's a trick question. Depends what version of the JDK you're using. If you're using JDK 8 or earlier, if you try to compile it, then run it, you'll get an exception in thread, illegal key size or default parameters. You'll probably get it confused. What's going on? You'll search the internet for an answer. And you'll go, aha, I need to download the JCE unlimited string jurisdiction policy files first. I need to install it. Try again. Then I run it. Everything works fine. So we had to do that for a long time because of US import-export laws on strong cryptography. I'm happy to announce that those regulations have been restricted, and as of JDK 9, we've enabled unlimited cryptographic policy by default. So now you no longer have to download the unlimited policy bundle. JDK 9 includes both the limited and unlimited policy files, and you can use the crypto policy security property to configure. However, the default value is unlimited. But if you want to change it to limited, you can. This means there's no limits on strength of cryptography. Out of the box, your application can use as strong as keys as it wants, and they will not be blocked. Most significantly, the most apparent change that will allow things like AES 192-bit and AES 256-bit to work out of the box. This change is also scheduled to be backported. Can I take questions at the end? Yeah, right here. It's done in 2 phases because we wanted to sort of mildly prepare you for it. In the October release, about 2 weeks, both policy files will be installed, but limited will be the default. However, it's just a simple switch of that property. You can even do it in your code, say security set property, crypto policy, unlimited, and then you're going to get it. So you don't have to download it. It's there in the JDK. And then in January, that default will be flipped to unlimited. Of course, I have to give a disclaimer. You are advised to consult your export-import control counsel or attorney to determine the exact requirements for your situation or region that you exist in. So I'm really happy to announce this. This was a huge pain point for developers for many, many years. So we're really happy that we've been able to do this. I'm going to go a little bit under the hood just for one slide to show you how the restrictions are actually configured. The restrictions are configured via security properties in the Java security file. There are 5 properties that we use to configure that. The first is JDK cert path disabled algorithms, and these are restrictions on certificates, CRLs, and OCSP responses. If any of those violate the algorithms listed in that property, they would be blocked by default. The second is JDK TLS disabled algorithms. These are restrictions on algorithms used in the TLS handshake protocol. What will happen here is that it will try to negotiate to a stronger cipher suite if it's available, but if the only cipher suites that are available are violate the restrictions in that property, then your TLS connection will fail. The third one is a little different. It's called JDK TLS legacy algorithms. Here, algorithms are negotiated in TLS handshake protocol, but only as a last resort, only if no stronger candidates are available. So as an example of one we have here is triple DES. Triple DES is known to be not really known to be used. It's on its way out. But because the interoperability compatibility risk is somewhat still negligible, we wanted to put it here. It's only used as a last resort, and then eventually we will put it into the disabled algorithms. Then JDK jar disabled algorithms are restrictions on signed jars. If they violate any of the restrictions, they're treated as unsigned. And the final one is JDK XML DSIG secure validation policy. And these are restrictions on XML digital signatures. These contain not only restricted algorithms, but also somewhat unsafe constructs that you can put in XML signatures, things like XSLT style sheets and things like that that are generally considered unsafe. So these are the default restrictions as of JDK 9 in the java.security file. The earlier releases should be pretty much the same, but I think there's a couple we're still in the process of backporting. I'm not going to go through this in a lot of detail. If you go to the Java security file, the syntax gives a really good description of how to use these properties and configure them. Obviously, I don't recommend removing any of the restrictions, but if you want to make them stronger or add new algorithms, this is actually one of the ways you can test things that are coming up on the roadmap. Then I definitely recommend doing that if you need to. And here's just a quick graphical example of how the restrictions would work. Here we have a cert path. It consists of 2 certificates, an end entity certificate issued to Alice and an intermediate CA certificate issued to CA2. The signature algorithm that Alice is using is insecure. So if we pass this cert path object to a pkix cert path validator, the validate method, it will then read the Java security file, read the JDK cert path disabled algorithms property, see that MD5 is in the value, and basically throw a cert path validator exception with that message. If you want a more debugging output to see exactly which certificate triggered that exception, you can rerun it and use the -d Java security debug equals cert path option. A couple other ways you can diagnose things. Key tool has been enhanced to warn you about weak certificates. If you use the print cert option, it will then emit a warning if the certificate is using an insecure algorithm, such as MD5 with RSA. Similarly, jar signer, you can use the -verify and -verbose options, and it will warn you if the jar was signed or digested with an insecure algorithm. Okay, that brings me to my next topic, which is to tell you about some of the exciting new security features in the just released JDK 9. So highlights, there are 9 new security JEPs in JDK 9. Overall, you can see significant cryptographic performance improvements, support for important new TLS extensions, ALPN, OCSP Stapling. We have support for new crypto algorithms, SHA-3 and DRBG, support for new protocols, DTLS, new restrictions on SHA-1 certificates, which I talked about earlier, and more secure defaults. The default keystore type has been changed from JKS to PKCS12. So here's a list of all the JEPs. I call this 9 for 9, because it's 9 features for JDK 9. This is mostly for reference. I'll go through most of these on the next few slides. So first, in the JCE or JCA layer, we've added support for SHA-3. So SHA-3 is a new family of cryptographic hash functions. It's based on the Keccak algorithm, and this was the winner of the NIST's SHA-3 hash algorithm competition. This was held over a span of about 5 years. I think it ended in 2012, and Keccak was declared the winner. And the standard is now defined in NIST FIPS 202. There are 4 variants, just like SHA-2. So there's SHA-3 224, 256, 384, 512, where the 512 is the size of the resulting hash. Now, to be perfectly clear, SHA-2 is still perfectly fine to use. There's nothing wrong with it. SHA-3 was created and should be viewed as an insurance policy in case SHA-2 is broken. It's based on a very different algorithm than SHA-2, so it's very unlikely that SHA-2 and SHA-3 would be broken at the same time. So now you have a drop-in replacement for one or the other. JDK 9 adds message digest implementations for all 4 SHA-3 hash functions, and more information is at JEP 287. Create PKCS 12 key stores by default. So this is very simple. In JDK 9, the default key store type security property has changed from JKS to PKCS 12. Why did we do this? For a number of reasons. PKCS 12 is stronger than JKS. It uses stronger cryptographic algorithms to secure the key store and its contents. It's also standards-based, so it's much more likely to interoperate with other implementations that support PKCS 12. And it has a richer set of features. So with JKS, you can only store certificates and private keys. With PKCS 12, you can store certificates, private keys, secret keys, and so forth. So it's a full-fledged key store. In JDK 9, KeyTool now creates PKCS 12 key stores by default if you don't specify the dash store type option. This feature had a little bit of a compatibility risk, so we recognized that early on we had to build in a compatibility mode. So right now a JKS key store can actually load a PKCS 12 key store and vice versa. This is supported in both JDK 8 and 9, and this essentially ensures that if you have existing code that is hard coding JKS, if you do like keystore.getInstance JKS, and suddenly the default is changed to PKCS 12, that code will still pass. It will be able to read a PKCS 12 key store, and you'll still be able to get the contents out of it that you need. And more information is at JEP 229. The next JCE enhancement is strictly a performance improvement, but a pretty significant one at that. Here we've used hotspot intrinsics to speed up the performance of GHASH and RSA. GHASH is the hashing component of the AES GCM cipher, and we've been able to improve the performance of AES GCM over JDK AGA anywhere from 34 to 150 times, depending on the data size. The larger the data size, usually the more performance improvement you're going to get. And I'll give you a little bit secret, it's actually higher than that, because in JDK 9, we snuck in a fix towards the end that improved the performance even more. So you might even see up to 200 to 300 times as fast as JDK 8. But this is what our public docs say right now, so I'm going with that for now. It's supported on the Intel x64 and SPARC architectures. And also in RSA, we did a modest improvement. We improved it by 10% on Intel x64. And more information is at JEP 246. The last of the JC enhancements for JDK 9 is called DRBG-Based SecureRandom implementations. DRBG stands for Deterministic Random Bit Generator. It's also known as a PRNG, or a pseudo-random number generator. DRBG uses a deterministic algorithm to produce a pseudo-random sequence from a random seed. So the security and the randomness of the seed is critical. It's really important for pseudorandom number generators. Now, this is a security improvement over the existing Java SHA-1 PRNG algorithm. It has stronger algorithms, a lot more options, and it's also based on a standard, so it's been more widely reviewed. The Java SHA-1 PRNG is a proprietary algorithm that was implemented in-house a long time ago. A little bit of the Java details. There's now a new secure random algorithm named DRBG, and we have implemented all three DRBG mechanisms: HASH DRBG, HMAC DRBG, and CTR DRBG. There are several new APIs in the Java security package for configuring DRBG mechanisms with different security strengths and options. And you can use the SecureRandom DRBG config security property in the Java security file to configure which of those three mechanisms you want to use by default. The default, if you don't do anything, is HASH DRBG. The seed source, by default, is specified by the existing SecureRandom source security property. And I don't recommend using the set seed method unless you really know what you're doing. Just use this default seed source. And more information is at JEP 273. Okay, over into the TLS area, we've got a couple of new exciting enhancements in JDK 9. The first is OCSP Stapling for TLS. So OCSP is one of two mechanisms that are commonly used to check the revocation status of certificates, the other one being CRLs. Now, typically, implementations use client-side OCSP checking, but that is problematic. It incurs significant performance overhead. The client has to make a network request to the OCSP responder, wait for the request, and then see if the certificate is revoked or not. Often OCSP responders become overloaded and can't handle the traffic. And because of this, most implementations have implemented a soft fail policy, where if they can't get a successful response over the network, they will consider the certificate is okay. The problem is that if an attacker can actually block that traffic to the OCSP responder, your security is essentially gone because you could block the fact that the certificate is revoked. So with OCSP stapling, the server is now responsible for obtaining and sending the OCS response to the client. This has several immediate benefits. The first is performance. Responses can be cached at the server and periodically refreshed and then sent to all clients. The second is functionality. So if you're using something like a captive portal in a hotel or a cafe to connect to the internet, OCSP client checking doesn't work because they can't check it until you have an internet connection. So there's a chicken and egg issue there. OCSP stapling solves that. And finally, privacy. With client-side checking, the OC responder knows exactly what server you're connecting to. With OCSP stapling, that's also addressed. OCSP stapling does not yet solve the soft fail policy problem, but I think it puts us on a road to eventually addressing that. Once most servers in the internet across the globe support OCSP stapling, then we can use something called OCSP must staple, and then the implementations can start to implement a hard fail policy. A few of the Java details. The Sun JSSE implementation supports the TLS certificate status request extensions, RFCs 6066 and 6961. It's on by default in the client, so the client always says, I support OCSP stapling if you're willing to send it back to me. It's off by default in the server because we wanted to make sure the administrator opts into something like that. You're making an outbound request to an OCSP responder. That's something the administrator should have control over. But it can be easily enabled. You just set this system property to true. And then there's a few other system properties that you may want to configure for finer configuration. And then more information is at JEP 249. TLS application layer protocol negotiate extension is also supported in JDK 9. This is an extension. It provides a mechanism for negotiation of the application layer protocol before the TLS handshake is complete. So the way this works is the client offers the supported protocols that it supports as part of the TLS handshake, and then the server chooses which one it wants to use. One of the main benefits here is it avoids an additional network round trip at the application layer to negotiate what protocol they want to communicate over once the TLS connection is complete. It also allows the server to choose which certificate it may want to use. So it may have different certificates depending on which protocol is being negotiated. This is specified in RFC 7301, and the primary or critical use case for this is HTTP 2. So I believe they require ALPN. ALPN allows them to determine what HTTP protocol is going to be used. And they're very happy that we've put this in. Several new APIs have been added to support this feature, and more information is at JEP 244. And then the JDK 9 TLS features is called DTLS. This extends the JSC API and implementation to support DTLS 1.0 and 1.2. So DTLS allows applications to use TLS over an unreliable transfer channel, such as UDP. Regular TLS is for reliable transport channels like TCP/IP. So an increasing number of application protocols are using UDP, things like session initiation protocol, electronic gaming protocols. So now we're providing a way for them to establish a secure session layer between their Java clients and Java servers, or any other servers. Applications use the SSL engine programming model if you want to use DTLS, and more information is at JEP 219. Okay, so I couldn't do a JDK 9 talk without talking a little bit about the module system in Jigsaw. You can't do it. So I have a couple of slides on some of the security features that brings. So first, all of our security components that I talked about earlier on that big slide have been modularized. These are a list of all the modules and the packages that they export and the service providers that each one of them contain. Java.base contains all your most common and useful security APIs. So you're going to get JSSC in there. You're going to get your Java security APIs, your crypto APIs, and most implementations of those as well. And then the others have been modularized as appropriate. The nice thing about this is that you can use JLink to now build an application in JDK with only the modules that you need. And this has a direct security benefit, is that you're reducing the attack surface area of the application that you then deploy. Some modules have been deprivileged. I don't know if you've heard of this, but some of the modules are now loaded by something called a platform class loader. And this allows them now to be granted only the required permissions they need. So if you're using a security manager, this is an example of one of our modules, JDK Crypto EC, and it's been granted 1, 2, 3, 4, 5 permissions. That's all it needs to do its job. It doesn't need any other permissions. Prior to JDK 9, this module or this component was granted all permission by virtue of being installed in the standard extensions directory. That's way too many permissions. Why does it need all those permissions? So this allows us to adhere to the principle of least privilege and only grant modules the permissions they need and no more. And then everyone's heard about strong encapsulation. If you're at the tech keynote, Mark Reinhold talked about it quite a bit. And here we're encapsulating most JDK internal APIs so that they are inaccessible at compile time. They're relaxed at runtime by default, but you can control that using the illegal access option. You can set that to deny so that they are inaccessible at runtime as well. Okay, conclusion. So overall, we continue to make Java more secure and incorporate new security features. Going back to those 2 goals at the beginning of the slide, I hope you come away with a strong feeling that we're continuing to make the JDK more secure by default and incorporate security features that help you guys build secure applications. But I want to give a big shout out to everyone here. You guys can help us. Let us know what you think is important. We're here to listen to you. Participate. There's a security group and a security dev discussion list. And if you're interested, you can work to becoming a contributor. I'd also give a call out for folks to come to my BOF tomorrow. It's going to be about the security manager. So if you love the security manager, you hate the security manager, you know nothing about the security manager, come along and we'll have an open discussion about some of the challenges associated with the security manager and what maybe the potential future of the security manager is. One other thing. JDK 9 Security Guide. I really recommend checking that out. It's been completely revamped. It's now all one guide instead of having like a dozen different guides, so it's easier to find things. And many of the features I talked about today have programming examples. I didn't have time to show examples today, so if you're looking to build those features into your applications, try them out. This is the best place to go for that. And then a few pointers to stay connected this week, different things you can check out. I have about 4 minutes for questions. I will just pop back that conclusion slide up just so you can. Any questions? Yeah. Yeah. How does it process it? How does it process the OCSP response? It's an extension that's attached to the server hello message. I think the server hello message, or one of the server messages that are in the TLS protocol. And then our implementation has been enhanced to actually validate that response according to the certificates that the server sends as well. Right, it doesn't have to. That OCSP response is signed. So it's signed by the OCSP responder. So you have to be able to validate that signature on the OCSP response too. Yeah. 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 Any other questions? Yep. I don't know. Well, I mean, the tool was so clunky to begin with that it was kind of embarrassing. So whether there'll be another tool, maybe someone will, come up with an open source project with a better tool. But it'll always be there. If you want to go back to JDK 8 and use it, you're fine to do that. But as far as it's still in JDK 9, but in JDK 10 or whatever it's going to be named, it's no longer there. Any other questions? Okay, thanks. I'll be out in the hall for a few minutes or up here until they kick me out.